All right, so now we'll go to lecture 9. One of my favorite subjects, talk about vector machines, vector supercomputers. Like last time we talked about branch prediction and load store queues. And those are kind of in this space of out-of-order superscalars. Those are ways of improving performance and dealing with memory system. But if we go back in time to supercompute, when the term supercomputer was coined, there's a set of calculations people wanted to do that were very compute intensive and kind of defined this space. And there were things like military research, nuclear weapons, cryptography, scientific research, things like climate modeling, weather forecasting. Another big financially important one was oil exploration. Also industrial design, things like car crash simulation. It's much cheaper to crash cars in a computer than to build them and crash them. Bioinformatics and now cryptography again. So these are kind of the biggest computations people do regularly. And the thing about these, they all involve huge computations on very large data sets. Right, so basically you just barely fit in these in available main memories. And basically supercomputers, the term was actually coined for the CDC 6600. That was so much faster than anything else, it needed a kind of a new name. So it became, this was a supercomputer, right? And since then, the kind of term has stuck for being the biggest, fastest machine in the world at doing a given task. And basically what's interesting is Cray basically held the title of the supercomputer creator for the several generations from the 6600, that was the fastest machine until the later machine, the 7600, and then Cray left and formed Cray Research, and the Cray 1 was then the next fastest super. So, and basically during the 70s and 80s, supercomputer was pretty much synonymous with being a vector machine, the vector supercomputer. So all the high-end machines were vector supercomputers. Now the Cray 1 that you'll be reading about for next time, this was really the kind of defined this genre of, there was a few earlier vector machines, but they were not very successful. The thing that Cray did with the Cray 1 is retain a very fast scale unit based on the RISC style he developed with the 6600 and the 7600. Whereas those machines were 60-bit and had 15-bit instruction units, he went to 64-bit and 16-bit instruction parcels in this machine and used that extra bit to basically have a vector version of each instruction. So, added an extra bit in the instruction, got the vector extension. And the big thing he did with here was he invented this idea of vector registers. And that really happened with the Cray 1. Very high performance, hardware control, highly pipelined functional units. The memory system was all static RAM based and very high performance and very highly interleaved. There was no data caches and no virtual memory on this machine. And this is a picture of Cray standing next to the Cray 1. This is the padded seat around the bottom you could sit on, and inside here was all the power supply for the actual machine. Actually, it was under there. This was also so the engineers could sit here while they're maintaining the machine. So one thing about these machines, they were very packed full of circuitry. These towers hold lots and lots of circuit boards horizontally placed in here, very densely packed, and the bars that hold them, refrigerant runs up and down here to keep the machine cool, to cool those circuit boards. And the circular structure was basically to keep the wiring short. And so if you look inside the middle of this C in here, you'll just see a whole mash of cables, like lots and lots of individual wires directly connecting boards to each other, sort of point-to-point wiring. It actually took 6 months to build one of these machines because somebody had to stand in the middle and basically hand wire every single connection. So from start to finish, 6-month latency to build a single machine. Also, it was pretty cramped in there, so they sort of handpicked small Wisconsin women, I don't know how many of them there are, small Wisconsin women to sit inside the machine and actually do this hand wiring. And every wire was measured to be a certain delay. So the length of the wire set the delay because it was a very high frequency implementation at the time. So this was sort of came out of nowhere again. This really surprised people. And this was a very popular machine. And actually, Cray Research during that decade was the fastest rising stock in NASDAQ because they were so successful building this machine and selling lots of them. So vector machines, how do you program them? Well, the vector program model is you have the, just an example vector machine. You have the regular scalar registers you would have anyway in a RISC style machine. But then you add these vector registers where each vector register can hold a number of elements.
How many elements depends on the machine architecture, and usually this is exposed in the ISA, but doesn't have to be. There's a concept of, there's a maximum number of elements that are present physically in each register. But a big difference with vector machines versus the more common these days SIMD machines is there's a separate vector length register that indicates how many of those elements will be activated when you issue a vector instruction. So if you set the vector length register to 1, only one element will do any work. If you set it to the maximum, then the whole vector register, you do an operation at every position in there. Okay, question?
Does that gate off the other functional units?
Well, so one thing the question was, does that gate off the other functional units? Well, a thing to realize is at the programming model level, you're not talking about functional units, you're just talking about operations being completed, as we'll see. So it just means that you don't produce results for the tail of the vector beyond the end of the vector length, the current vector length, right? And so you can use that to gate off the functional units or to reduce the time it takes to execute the instruction. So a vector arithmetic instruction is defined as being, pairwise parallel across the whole vector. So every element position, you do an addition here, for example, across the whole length. So a single vector add instruction does a lot of work potentially. In vector machines, you can do actually hundreds of operations with a single instruction. Vector load and store instructions come in several flavors. One example is a strided vector load, shown here, where you have a base address and a stride given in scalar registers. So the base address is just a scalar base address. The stride is the distance between the elements in main memory. So when you do a strided load, it starts at the base address and then picks up elements separated by the stride, but then packs them together to live in contiguously in a vector register, right? So this is a gather style instruction, except this is a constant stride version. So to look at what does vector code look like, let's compare it with scalar code for a simple loop. So here's the C code for a very simple vector-vector add loop. Just add A, I, and BI corresponding elements and place them into CI. If you look at the scalar code, what you do is you load the loop count. You then do the individual scalar loads of 2 floating point elements, do the floating point add, store the result, and then you bump the address pointers, decrement the loop counter, and go back to the loop. Right, so that's a simple scalar loop. The vector version is you get the loop count, set the vector length register, load the first vector, load the second vector, do the vector add, and store the vector result. So if you look at the difference in terms of instructions fetched in the scalar code, you've basically fetched 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions for one element, and then you do that 64 times, right? So 64 times 9 instructions are fetched, plus the one at the top to initialize the loop. In the vector code, you fetch 6 instructions total. Now notice that the instruction bandwidth has been reduced for 2 different reasons, right? One reason is that obviously these are vector instructions, so one operation does a whole vector of things. However, the second thing is that these instructions sort of fold in a lot of the bookkeeping that you do separately here. So implicitly here, where you do a unit stride vector load, you're implicitly calculating all the intermediate element addresses. Whereas in the scalar code, you're explicitly bumping the pointers to calculate those intermediate addresses, right? Also, the loop counting and decrementing and branching, that is kind of implicit in the fact you're doing a vector of operations. So you're not doing these loop decrements and branches either in the vector code. So very dense in terms of really reduces instruction bandwidth. And in that period when these machines came out, that was seen as one way around what they imagined was the Flynn bottleneck of only doing one instruction per cycle. You could do one instruction, but it could do a lot of work in that one instruction. Question?
In this particular vector version, if the vectors you're operating on are longer than your vector registers, is that handled implicitly in kind of a CISC-esque way?
So the question is, what happens if your vector is longer than 64? That's a good question, and we'll get to that in a minute. Okay, so let's just take a look at the Cray 1. So this machine had a set of pipeline functional units that were actually the floating point unit here, add, multiply, and reciprocal, which was used to implement divide. These units were actually shared between the scalar and the vector units. So here's the the main scalar registers, data registers, S0 through S7, so you had 8 of those, and here are the 8 vector registers, which in the Cray one had 64 elements each. So other functional units are also shared between the two sides. Separately, there was actually a set of address registers, kind of like on the CDC 6600, the same notion of on these machines, data was 64 bits, but address was much less than that because main memory in this machine was only on the order of a megabyte, so they didn't need as many bits, and it was addressed as words, so they didn't need as many bits in the address register, so these were smaller and separated out to these address registers. And they had some separate address functional units there as well. It was a register, load store machine. In addition, they actually had backup registers, so as well as these foreground registers which could be used by any arithmetic instruction, there were backup registers which actually formed an explicit register hierarchy in the machine. So you only had 8 foreground registers you could use in an arithmetic operation, but you can move to and fro between a backup register file, which for the S registers was called the T registers, for the A registers was called the B registers. And this let you, the compiler would schedule the moves to and fro, to basically register spill in and out of here. And also subroutine call return, you could actually move a block of registers between the T registers and main memory as a burst of loading and storing multiple registers at a time. So there's a very small instruction buffer, which was like an instruction cache. The main memory system, though, was one of the more impressive things at the time. It had 16 banks of SRAM memory with error correction, and it could support 1 word per cycle, 1 8-byte or 64-bit word per cycle at peak rate load and store. Interestingly, they could actually get higher bandwidth during instruction cache refill. They could actually burst through it quicker, but for data it was 1 word per cycle out to main memory, and that's for all of main memory. So 1 word per CPU cycle out to main memory, and this thing ran at 80 megahertz, which was far and ahead of anything else at the time. So one thing to know about this machine, it introduced the idea of vector registers and this kind of vector processing, but also it was the world's fastest scalar processor as well. Nothing else was close to this in terms of scalar performance. A lot of machines are bought because of the scalar performance, and people just ignored the vector unit. They just wanted the scalar performance from this machine. Okay, so vectorize advantages. It's very compact, right? So, one short instruction encodes a lot of operations. And we'll contrast that with VLIW machines we'll talk about next. But here, basically, a very short instruction can encode a lot of work. Also, it's very expressive. You're basically telling hardware, when you use a vector instruction, that the n operations inside the vector instruction, they're all independent. So there can't be any hazards between all those operations that you're doing in one vector. You're also telling the dispatch unit that all these operations use the same functional unit, right? So you don't have to, is this an add, is this a multiply, is this a load? You know they're all the same. You also know that if you design your vector ISA properly, that at each element position in the vector, the operation that's being done there is going to access different registers than any other element position in the vector. I'll describe how that's important in a minute. Also, that every operation will access registers in the same pattern as all the other operations. The point here is you're not doing sort of random scatter gather within the register file. It's very constrained where each vector element is picking up its operands and producing its results. So another thing, when you're doing loads and stores, the vector loads and stores kind of tell the hardware that you're going to access a big chunk of memory. So when you do a unit stride load or store, you're telling the memory system, look, I want a big block of memory. Go get that big block of memory. You don't have to guess or speculate about getting a whole bunch of memory. The instruction tells you, go get me a lump of memory. Or if it's not just contiguous but has a fixed unit stride, you're also telling the memory system, go get me these memory at these different locations. And another big advantage of vectors is that it's a scalable ISA. And I'll describe what that means in a minute, but basically you can have the same binary assembly code run on different machines that have different numbers of functional units and different levels of pipelining or parallelism, right? That's quite an important advantage. So let's look at how you build a vector machine. So one advantage is there is no hazards between the operations in a single vector instruction. They're all independent of each other. And so a lot of the vector machines actually made use of this to build very deeply pipelined functional units. And it's quite common for the vector unit to run at 2 or 3 or 4 times the clock rate of the scalar unit by using very deep pipelines. And so you get this very high performance in very little logic. And you basically just stream elements out of the vector register file through the multiplier or some other function unit back to the destination result. Okay, so you can build very deep pipelines because there's no hazards. And when you execute at the assembly level, you write something like this, vector floating point add, VC gets VA plus VB. And if you have a single pipeline functional unit, you just stream the operands through like we just described. So here's the results, C0 coming out as I pipe in more elements from A and B, just going through one pipeline. But the same assembly instruction, you can execute on a vector unit that has many parallel functional units. So in this case, I'm producing 4 words per cycle of result. But notice I haven't changed the instruction encoding. So contrast that with what you just read about in Haswell, where if they went from 1 to 4, they have a whole new set of opcodes saying do 4 at a time, do 1 at a time. The vector style ISA, there's just one instruction that says do the vector operation, and it's up to the microarchitecture to figure out how it wants to do those in terms of being parallel, the pipeline. So the same assembly code runs on both these hardware architectures, right? So because you give the memory system a lot of knowledge about what's going on, you can build very highly pipeline memory systems as well. And again, you also have the advantage of knowing there are no hazards between those individual operations going to the vector memory system, because you said by using the vector instruction that they're independent. So it's very common for the vector supers to have very highly interleaved memory systems. So the Cray 1 had 16 banks of SRAM, static RAM, where each bank had a 4-cycle bank busy time. So that was the occupancy. So when you made a request to a bank, it took 4 cycles, it spent 4 cycles in that bank, and the bank couldn't be used for another memory access until 4 cycles later. Overall, there was a 12-cycle latency from when you initiated a load to when the result came back to the register, including getting through the interconnect and back again from the memory system. So the Cray 1 had an address generator, so when you issued a strided load, it would capture the base address and capture the stride, and then this unit would just run ahead and calculate the individual elements' addresses and send those down to the memory system. Now, with this interleaved memory system, you have to worry about getting bank conflicts, right? So in the best case, if you're doing unit stride accesses, you know that you're going to move sequentially across the banks. And so, it'll take you 16 banks before you get back to the first bank, and clearly then you'll be ready for the next request. It's only busy for 4 cycles. Okay, so what's the worst case stride on this machine? 16, right? So if you had a stride of 16, you would first fetch one element from bank 0, for example, if that was the base address in bank 0. Then the next element would also be in bank 0, and so we'd have to wait 4 cycles. So you'd only get 1 word back every 4 clock cycles. So it turns out any multiple of 16 would be bad, right? So any multiple of 16, you'd be continually hitting the same bank in the memory system. Okay, what are other bad strides? 8, right? So if you have a stride of 8, you're going to basically ping pong between 2 banks. And how fast, what would your throughput be relative to peak then? Half. It'd be 1/2, right? So 2 banks, each of them has a 4-cycle bank busy time. So on average, you get 1 word every 2 clock cycles out of the main memory system, right? So it turns out multiples of 8, multiples of 16 are bad. Multiples of 4, what happens then? So multiple of 4 is fine, right? Because you cross 4 banks. By the time you get back to the first bank, it's ready again for another access. So only multiples of 8 and only multiples of 16 are bad. So programmers got used to actually coding for these bank conflicts. And so they would actually artificially pad the arrays. If they wanted a 256 by 256 array, they would actually write it as 257 by 257 and not use the extra row and column. And that way, they'd avoid the bank conflicts, right? The way the array would be laid out in memory would avoid the bank conflicts to get better throughput. So the vector units, so getting back to this property, vector instructions, each operation only accesses operands at the same element position. So if I'm doing a vector operation, element 0 in the vector will read operands from element 0 of the source vectors and write its result to element 0 of the destination vector. And this is important because it allows you to slice up the functional unit into these parallel lanes, right? So you take the register file, the total storage you need for all the vector registers, and you divide it up into chunks, and you just stripe the elements across these chunks. So all the element 0 of all the different vector registers live here, as does element 4 to element 8. Elements 1, 5, and 9 of all the vector registers live in this second lane, in this second slice of the vector register file. Okay, so you have this, this lane structure, which is the repeated, physical structure that's just replicated. But when you issue a single vector instruction, it activates an entire vector functional unit, and the functional unit crosses all the lanes, and so this will in one cycle do elements 0, 1, 2, and 3 on one cycle. The next cycle it's going to do elements 4, 5, 6, and 7 across the lane. So one vector instruction runs all these functional units in lockstep across all the lanes, right, to get higher throughput. But notice that the wiring here, all the read and write ports are constrained within a single lane. You don't have read and write ports crossing each lane can access any slice. It can only needs to access this local slice. It's very efficient in terms of wiring. And the only global wiring between these lanes is through the memory system usually. So there's a path to load and store from any address in the memory system into any lane. But this is the only crossbar-like structure. The rest of the wiring is really constrained within the lane. That's what makes it very efficient. So even though you're doing many operations per cycle, you don't need a huge number of ports on each bit of the register file. It's divided amongst the different slices, these lanes in the vector unit. So this is physically, showing you what this looks like. This is actually my thesis chip. I built this thing here at Berkeley a long time ago, 95, 20 years ago, I guess. So here's like what a lane laid out on the chip. And you can, this thing had 8 lanes. So those are the 8 lanes. This is actually the crossbar that connects the lanes to the memory system. Here's the scalar processor, here's the instruction cache, the control logic. And this is the way the vector registers are striped across. So all element zeros live here, 1, 2, 3, 4, 5, 6, 7, and so on, right? So you can see it's very clean, simple layout in this design. Now, what's interesting, if you look at how instructions execute on this vector machine, when you issue a single instruction, it can encode a lot of work. So in the T0 example I gave there, the vector registers were 32 elements long. So when you issued a load instruction, that would issue in one cycle to the load unit, but it would tell the load unit to load 32 elements. And it would load them at the rate of 8 elements per cycle. So this load instruction would run for 4 clock cycles, keeping the load unit busy for 4 cycles, fetching in total 32 elements, right? But on the next cycle, you could issue something to the multiply unit. So a single instruction issue to the multiply unit would get that going, and that would do another 32 elements at 8 elements per cycle, but it'd be overlapped with the finishing off of the load instruction. And then in the next cycle, you could do an add, and then you would come back around a couple cycles later and start off another load instruction, right? So in this way, once the machine gets going, in this case, you're doing 24 operations per cycle, but you're only dispatching a single 32-bit instruction per cycle in order to get this much parallelism in the machine, right? So it's kind of like spinning plates. You kind of go along and you spin this plate, and then you go spin this one, you go spin this one, and they keep going for a little while just to make sure to get back often enough to give each unit enough work to keep it busy. But it means you can have a very small instruction issue unit and get very high degree of parallelism, right? So now we'll sort of switch over to talk a bit about the different techniques people have built up around vector machines. That's the basic idea of how vector machines work. So with the Cray 1, Cray actually introduced this concept called chaining, which is just a vector version of bypassing. So you're familiar with bypassing for scalar machines. If you look at this little snippet of code here, I'm doing a vector load into vector register 1. I'm doing a multiply using v1 as one of the arguments to produce a result v3, then adding v3 into another register with a vector add instruction. So there's dependencies here. Now in sort of classic scalar design, you would do the load, it would then complete. Once the value was ready, you would then do the multiply till it was complete, then you would do the add. But the thing to notice in the vector form, each element instead of viewing the whole register as being completed, you really can start work on the next instruction as each element within the vector is completed. So this element by element bypassing is what's called chaining. So in the Cray one, you'd have the memory system go into load unit writing into V1, but rather than wait for the whole thing to be written, as each element was produced from the load unit, they would chain it into the multiply unit, and so get started with that next operation straight away. And as the multiply produced results, you'd pipeline that into the adder and get that started straight away to write back into vector register V5. So now one interesting thing that Cray noticed was when he built his vector registers for the Cray 1, he used single-ported memories, single-ported SRAMs, where each vector register was held in a different set of SRAMs, but with only a single port that could do read or write. So each SRAM could only do a read or a write, not both, and not multiple reads or writes. Now notice here that I'm doing this whole chain, lots of operands are flying around, but each individual vector register has only got one read or write going on. So he's making use of the trick that once this value is produced by the load unit, I write it to V1, but instead of having a separate read port in this memory structure, I pick it off before you get there. So this is just using the bypass to produce that value. I'm not requiring a separate read port for the multiply result. Similarly here, you're just using this value. Okay, so this is a nice trick, but there were a few constraints here. One was if you did this load, and then say you got an instruction buffer miss, and you had to go fetch the multiply instruction from a memory, it may show up too late, and the value's already been written into V1 before you dispatch, before you issue the multiply instruction, right? So in that case, what do you think would happen? Right, so you'd have to wait until the load finished, and then you would start the multiply reading from V1, because it only had one read or write port on the vector register file. Okay, that's one problem. That was a thing they call the chain slot time. If you missed that window, you just have to wait till the very end to then go get the values, right? If you were too late showing up for the first element. Now, the second problem is even more subtle, is what if this add was actually an accumulate? So I want to add a vector register to another vector register and store the result in the same vector register. So say this was add V3 to V5 and store it in V5. What's the problem and what should I do about it? So I want to read and write the same vector register in the same instruction, but I only have one read or write port on the vector register.
Some temporary storage to buffer the, yeah, you need somewhere else to temporary status hash the result until you write back in the same register. Right?
Yeah, so one possibility is you have some extra storage to hold the result. Cray wouldn't do that. That's just too much stuff. What's another solution?
You don't allow it to
Delete the write.
Sorry.
Delete the write, I mean, read first and write later.
So another solution might be you interleave and you go half speed. You do a read and then a write and a read and a write. That's kind of complicated, so Cray wouldn't do that either. So what's another alternative? So don't allow it. That was another alternative. That's kind of what he did, except they didn't actually not allow it. It actually just, they just ignored the problem and the machine would run. And it did an interesting thing. So what it would do, it would actually recirculate the value writing back, came back in as a read operand. And people found this actually very useful because they used it to do accumulation. So what you would do is, in the normal case, you weren't allowed to have the source operand be the same as the destination. You had to go to a different register. But when you are reducing a vector to a single scalar value, you want to add all the elements together. You would first run through the big loop doing strips of values till you got one 64 element vector that you then had to reduce. You would then do this add to itself, and what would happen was the pipeline latency was 8, and so you'd actually get 8 results at the end of the vector register that were the sum of the every 8th element, 8 individual accumulators, one for every 8th element in the vector register. Then you would dump out those 8 elements and just sum those finally in the scalar unit. So it's actually a fast way of doing reductions that was kind of an accident in machine design. But programmers figured this out. The later Cray XMP, they kind of fixed this problem by having real read and write ports on every vector register, but then programmers complained that they couldn't do reductions fast anymore, so this hack had gone away. But that's what they did. But basically, there's physically only one read or write port in each of these SRAMs. Okay, so the nice thing about chaining is, graphically, instead of having to wait for the whole thing, you can overlap, right? So the different, and what you're getting here is vector instruction level parallelism. So multiple vector instructions are in flight at the same time, overlapped. Even though you're only issuing one instruction at a time, right? You're still getting vector ILP. So some of the details about vector design. One thing you have to worry about is vector startup time. So the vectors emerged in the period where they're really doing very pipeline vectors. And so latency in terms of clock cycle was important. Now, if you start reading about vector machines, you'll read a lot about startup latency and the issues there. But it's important to separate, there's two components to it. One is functional unit latency, the time it takes for the first result to come out of the vector pipeline. So this example, I have a read of the registers, vector registers, 3 cycles of execute, and write back of the result, right? And so this is just showing you in the pipeline diagram the elements of one vector instruction going down some functional unit, right? So, it's clear you have to wait for the functional unit latency before you can get a result. Unfortunately, some of the vector machines had an additional delay between one vector instruction and a second vector instruction, where there was what's called dead time. Even if these two instructions were independent of each other, there was no data dependency, and there's clearly no structural hazard between them, you still had to insert, the machine would just interlock and wait for this dead time between those two instructions. And during this dead time, the vector function unit is basically idle. It's not producing any value. So anybody, an idea where this came from? Why would they do this thing of waiting before they push another independent instruction down the vector pipeline? Control. Right, actually, it's the control logic. So the problem was, remember we said vector instructions were nice. You knew there was no hazards, and you could deeply pipeline those vector units. In the simple vector machines, they didn't actually have a separate instruction register for every stage in the pipeline. There's kind of one at the front that says what the pipeline is doing. So what this is all about is kind of draining out the pipeline so you could change a register up front that told the pipeline what it's doing. Is it doing an add or a subtract, for example? So it's actually just, as seen here, I'm just waiting for the write to clear out so I can flush out. This is the last guy that's doing an add, for example. This will be the first guy doing a subtract. So that's really kind of limitation of how they built these early vector machines. They just had this very deep pipeline with a single register indicating all the control for that entire pipeline. So they didn't pipeline the control along with the data. There's no reason. Now the problem is, as people started building wider vector machines with more lanes, we only had one lane. It was kind of okay, because given vector lengths, there's just a few cycles to flush the functional unit pipeline, then you would run for 64 cycles. But as you start adding more lanes, the cycle time, the dead time becomes more problematic. So one later machine, the Cray C90, had 2 lanes, 128 element vectors. So it turned out that even with the longest vectors, with this 4 cycles of dead time, the maximum efficiency you could ever get is 94%. Perfect code would give you no more than 94% of peak performance, right? Because of this dead time, right? So turns out there's no real reason. If you have more sophisticated control logic, you can avoid that dead time completely and basically saturate the functional units even with very short vectors. So on T0, the chip I did, 8 lanes, no dead time. Even if you had 8 element vectors, you would issue them back to back, just as you would expect coming from scale-up processor design, right? It's just kind of a hangover from the earlier vector machine designs. You'll see this kind of problem showing up. Okay, now the very first vector machines were actually the CDC Star 100 that was done at CDC after Cray left, and Texas Instruments Advanced Scientific Computer, ASC. These are sort of at the end of the 60s, beginning of the 70s was when these were designed. And they were what were called vector memory machines. So people had the idea that you want to work on vectors, and they had vector instructions, but those vector instructions actually read and wrote vectors directly from memory, not through registers. So if you took a loop like this, which is just adding A and B to C, subtracting A, B from A, putting into D, on a vector memory machine, the code was really simple. It's like just add A and B and put it into C. And the operands would be the scalar registers given the base addresses of these vectors in memory. So it's like direct memory access, go straight to memory, streaming the values through the operation, streaming results out to memory. Okay. Whereas vector register code, you had to load a vector strip into a vector register, right? Then do the add inside the registers and store the register out, and then do the second subtract here again, and so on. So this was a lot more instructions to do the vector register version. But why is the vector register version superior?
Faster, you don't have to go to the memory twice.
Right, exactly. So the advantage of the vector register machine is operands A and B, you only fetch them once. Put them in vector registers, and then you can get the reuse out of the registers for these two operations. The add and the subtract both use V1 and V2. So that was the big advantage of vector register machine, was just reducing the memory bandwidth you needed. The vector memory machines had really amazing amounts of memory bandwidth because they needed it, because every operand would come in and out of memory for every operation, right? So it's really inefficient. So basically, after Cray 1 came out, any subsequent machine was vector register. That was you just didn't build vector memory machines. Only these guys who had to maintain compatibility with the earlier machines kept doing vector memory architectures, but that was a big penalty for doing so. So just talked about this. Another problem with memory architectures is that it's actually difficult to overlap multiple vector operations. And why is that? What's harder about memory architectures versus vector register architectures in terms of vector ILP? Having multiple vector operations in flight. Well, one would be the structural hazard on the memory system. You need even more bandwidth. But what's worse than the structural hazard?
The memory regions could overlap, right?
Right, so the problem is the data hazard. So now you have to look at all the addresses in those vector instructions to figure out if there's data hazards between those vector operations. Whereas if you're working on vector registers, as with the scalar machines doing register, you just have a few bits to look at to determine any dependencies between the operations. There was also this issue about startup latency you hear a lot about. And so this wasn't quite just due to the memory going in and out to memory the whole way, though that was part of the story. But what was interesting was the first vector machine, the Star 100, it was only faster to use the vector unit if you're working on elements that are more than 100 elements at a time, because the time it took to get the thing going, do a vector memory operation. Whereas on the Cray 1, basically, like about 2 to 4 elements, it was faster on the vector unit on the scale unit. So the compiler had a very easy time of it. Basically, if you saw a loop, you ran it on the vector unit. So it was a very easy thing for the compiler to do, and that would generally be faster.
Isn't this like an echo of the RISC versus CISC debate?
An echo of the RISC versus CISC debate.
Because this is memory versus register.
Yeah,
Load store.
that's right. It's similar to that, yeah. I think the CISC, the complex part of it wasn't quite there, because a lot of the vector, but yeah, the notion that the operands, where are the operands? You want to have them in registers, not have them be arbitrarily in memory. That part of it is the same, yeah. Same argument. Yeah, so everybody used vector registers. We kind of basically ignore vector memory from now on. So one of the challenges of vector machines is you have to generate code for them. So if you look at automatic code vectorization, the semantics of this piece of C code is you do the iteration sequentially. So in order to generate vector code for it, which would do this load and this load in parallel in one instruction, and then this load and this load in parallel in a second instruction, and then the 2 adds in parallel in the third instruction and the 2 stores in parallel, is that you've effectively done a massive compile time reordering of all those operations, right? So your vectorizing compiler has had to figure out that it's okay to not do this store until down here, and that this load doesn't depend on this store, for example, and there's no other dependencies through memory between those iterations, right?
Has anyone ever tried having like special instructions, like you emit both types of code, the scalar and the vector, and then you check at runtime if there's a dependence?
Yeah, so the question is, have people tried doing dynamic dependence checking? Yes, there's actually software techniques, vectorized software techniques that will detect hazards in between loop iterations, and those are commonly used when you have scatter-gather kind of code. It turns out you can quickly vectorize the checks to see if any of the iterations are dependent. It's not as fast as knowing there's no hazards and just emitting the code, but it's a lot faster than doing the scalar loop. Yeah, but there are techniques in software to do that. So getting back to the earlier question, how do you handle vectors that are longer than the vector register? And that's just this concept of strip mining, like from quarrying. You take a chunk, then you move over and do the next chunk. So here's like kind of the picture of it. Say I only had 64 elements in my vector register, but my loops were longer. So this piece of code, what I'm going to do is calculate the remainder just by doing an AND operation. Like this is how many elements are in this little piece that's left here. You know, some less than 64 elements here. I set vector length register to that. Then I go through the loop. I do a loader strip here, do the add, do the store. In between, I'm calculating the pointer offsets. Subtract out the number of elements I did this time through the loop. So the first time through the loop, it'll be something less than 64. But then down here, the next time through the loop, I just set the length to 64 and just iterate around the whole chunks of 64 at a time. So right in this strip mining loop, I can iterate on any length vector register. Now notice within each strip mine loop, if the body of this code had several statements that reused vector operands, I could reuse those through vector registers within that one iteration of the strip mine loop. Then the next iteration, I move over to the next set of elements in memory vector and do the same things on those, right? So that's strip mining. So the other thing to talk about is conditionals. So code has ifs and thens and takes branches. So in vector machines, the solution people came up with was to add vector mask, or sometimes flag is what they call them, flag registers. And this is just a vector version of predicate registers, where there's 1 bit per element. And basically you mask off the ones you want to do, and where the mask is clear, you just don't do the operation at those element positions. So here's a simple example. This instruction is clear vector mask, so it turns on all the elements actually, so nothing's masked. You do a load, this is doing this code unit. I'm going to load the A vector, so this will effectively load everything because the mask is all on. And then do an operation that does a compare that sets bits in the mask register where elements are greater than 0. Then I only load B where the mask is true, and then I only store A where the mask is true. So I've omitted the elements where the mask is clear. Now one detail to get right here is to make sure you don't cause any exceptions on where the element operation is predicated out, right? That's a thing you have to do in the vector machine design. So a simple way of doing this is, if you think about a single pipeline, you just pipe the mask bits down the pipeline as well as all the elements, and when you get to the write back stage, you either write the result or you don't. And also you either report the exception or you don't for each element as it goes through. There is people who talked about doing density time implementations where you actually compress out the zeros. So you don't do the work if there's nothing to do. This has a bunch of implications on how well you can actually do this in a real microarchitecture, depending on when these bits become available in the machine, and also the complexity of actually doing this compression. But people have done that in real machines. I'm going to skip over this in the interest of time, but people have added a bunch more instruction types to vector instruction sets to improve the range of things you can vectorize well. One example is compress expand. We can, just where the mask bit is set, pull out those elements, then do shorter vector operations on the active elements, then expand it back out again. We talked about vector reductions, the Cray 1 style, and this is very common in code. You just want to sum all the elements in a vector. So the classic way you do this in a vector machine is for a sum reduction, you just sum up. You keep 64 partial sums as you step through the vector. Then once you get to the end, you just reduce those 64 down to a single value. Now one thing is this will give you, because of floating point being non-associative, you're going to get different results than if you've done it on a scalar machine. Doesn't mean better or worse, just different than doing a scalar reduction because the adds have happened in a different order. Okay. So just quickly go through scatter gather as well. So very powerful thing of vector machines is being able to vectorize loops with indirect accesses, right? So here C is being indexed by a data value held in DI, right? C of DI. So using a gather instruction, you would load indices from D into a vector register. Then the indexed vector instruction would take a scalar register as the base of D. Yeah, this should be VD here, yeah. This should be VD. Okay, so what this slide should have is, you load the elements into indices into VD, which is a vector of indices. You then do an indirect address where you add the scalar base address XC to the indices held in the vector register VD, and that's the gather into vector register VC. Then you load the B vector just as unit stride, do the add in vector registers, and then just store out unit stride there. So the gather just compacted things so you can combine them with the regular operations. Okay. So let you, in your own time, look at this, how you do histogramming and what the problems are. This is an example where there are hazards potentially between loop iterations. depending on data values. And if you did the naive translation, you could get the wrong result. It turns out you can do a vectorized comparison that will find the problem cases for you. I'll come back and revisit that. Just to finish off, so this is an example of a modern vector supercomputer. People still make these. There's still applications where these are much, much faster than scalar machines. It's a relatively old one. There's a new one that just came out like last year, SXACE. So NEC continued to build these. Just to give you an example of the performance of these things. You know, vector unit runs at 3 gigahertz, which is kind of comparable to a fast scalar processor now, but has 8 lanes. So there's 8 parallel execution units. So we can do over 100 gigaflops peak per CPU. Now the more recent, say, Intel machines are getting close to that kind of performance, but what really sets the vector machines aside is the memory system. So here, each CPU has 256 gigabytes a second of main memory bandwidth, which includes gather-scatter bandwidth out to that DRAM. And what's more, you build a node that has up to 16 CPUs, where each CPU has 256 gigabytes a second of bandwidth with the same shared memory. So you have over 4 terabytes a second of bandwidth to that shared main memory where all the vector units are plugging into that, right? So that's really the performance difference is very high main memory bandwidth, and the vector unit load stores to actually drive that main memory bandwidth to get data in and out. So these are very specialist machines, but they're still being made. Okay, that's it for this time.